So this is where we left off last week. We left off with surface of revolution and surfaces of revolution. And basically you can think of it as surface area if you want to. And I did get you to write those formulas on your page, yes? And like I said, if you want to print off the new Chapter 6 formulas page, they're already on there. Just to alleviate you copying anything down wrong. But the only difference between these formulas and your arc length formula is the 2 pi times your function. And then the rest of it is the same. The fact that you have the square root of 1 plus your f prime squared. So, and on this, you just need to remember that if we are revolving about the x-axis, you need x boundaries and x stuff. And if you're revolving about the y-axis, you're revolving around y boundaries, and you need y stuff, like y variables. So, we did this problem. It wasn't that bad. The nice thing about this is your boundaries are pretty straightforward. Just remember, the problem itself tells you which formula you're going to use. If you have y equals, it tells you that you're going to use that formula. If it tells you that you have revolving about the x-axis, all you have to do is go to your formulas page and go with that. Okay, so let's look at this one. It says find the area of the surface generated by revolving the graph of x equals 4 times the square root of y from these 2 points about the y-axis. Now, since we're going about the y-axis, your formula, and I'll just be straight and honest with you, I don't know the formula by heart, so I have to cheat, and I would advise you to do the same thing. Your surface area is going to be S is equal to the integral from C to D, and I know that because we're going about the y-axis. And then you have 2 pi g of y, don't let that throw you off, it's still your function, times the square root of 1 plus g prime of y, that's your derivative, squared, and then of course dy, respect to y. Alright, so let's try to plug in. So we're going to integrate from C to D. What is C and what is D? Very good. We're going to go from 1 to 9. And then 2 pi comes from your formula. What is your g of y function? Yeah, 4 square root of y. And then times your square root of 1 plus. Now we don't know what the derivative is yet, right? So let's go off to the side and figure out what the derivative is. If g of y is equal to 4 square roots of y, but I'm going to change that to the 1/2 so that I can take the derivative, then g prime of y is going to be what? 2y to the negative 1/2, is that what you came up with? Okay. So we're going to plug that into our formula. We're going to have 2y to the negative 1/2 squared dy. And that's your setup. From here on out, there's some algebra that you need to do, a lot of algebra actually, before you even take the antiderivative. So make sure you can do that, that integral. The 2 pi, I'm going to move out front because it's a constant. It's just a number, 2 times 3.14, blah, blah, blah. Integrated from 1 to 9, you can leave that 4 square roots of y the way it is, or you can change it to the 1/2 at your choice. 1 plus, this is going to be 4y to the negative 1. Okay, dy. Okay, when you see that 4y to the negative 1, what does that make you think of? That's going to turn into what? it's going to turn into a fraction, exactly. So we're going to have 2 pi times the integral from 1 to 9. Now I am writing every single step. If you don't need to, don't worry about it. You don't have to. But I don't want to lose anybody, so. Now, based on what we did last Monday, what did we do from here? Do you remember? Yeah, we made it into one fraction. Good. So that's going to be what? Y plus 4 over y. Is that okay with you? If I write it like that? Or do you want me to go back? I did skip a step, and I just told you I wasn't going to, didn't I? Okay, I'll go back. Right? Because, and again, I'll go over to my scratch paper. If I have 1 plus 4 over y, I need a common denominator, and that 1 turns into y over y. And now I can put it together. Does that help? dy. Okay, one more time. So we're going to have 2 pi integrated from 1 to 9 of 4 square roots of y. And I'm going to bust this up now. I'm going to take the top over the bottom. Do you see anything that I can do at this point? Keep in mind, this is multiplication, and if you need to, you can put that over 1. Do you see anything I can do? Any ideas? Yeah, the square root of y cancels the square root of y. Very good. Well, that leaves me with a constant of 4. What do you think I can do with that? Yeah, all your constants can come out front. So I'm going to bring this 4 out here. So this is going to turn into 8 pi times the square root, or times the square root. 8 pi times the integral from 1 to 9. And then if you want to do square root of y plus 4, you can, but I'm fixing to integrate, so I'm going to change that at this point. I know that I'm fixing to integrate. Okay, so let's go back to our Cal 1 days. In Cal 1, if you have y plus 4 to the 1/2, if you have a group to the 1/2, when you take the antiderivative, we don't have the chain rule. We don't have the product rule. We don't have the quotient rule. So what do we have to do? Very good. Use substitution. So if we let u be y plus 4, this is not good. Okay, so u is equal to y plus 4, so du is going to be equal to what? Oh my gosh. Yeah. Okay, so let's go up here. Get a little more room. So if we have 8 pi times the integral from 1 to 9 of u to the 1/2 du. What's that antiderivative going to be? What's the antiderivative of u to the 1/2? Very good. U to the 3/2 over 3/2. And we're going to go from 1 to 9. Now what am I going to do with that 3/2? Alright, so we're going to have 16 pi over 3 times u to the 3/2 integrated from 1 to 9. Now, if you want to change your boundaries, you can at this point, just by plugging 9 back into the y plus 4. Or you can just do the math. For this problem, it's not that bad. So if we have 16 pi over 3, now listen to what I'm going to do, okay, because I'm not going to write it down. You guys have been doing this enough, you should be able to know how to do this. I'm, in my head, going to take that 9, and I'm going to plug it into u. So if I plug 9 in for y, 9 plus 4 is going to be what? 13. So that's going to turn into 13 to the 3 halves. Minus, if I take that 1 and plug it into the u, 1 plus 4 is going to be 5. So that's going to turn into 5 to the 3 halves. Or if you want to change your variables, you're doing the exact same thing. Okay, start punching on your calculator and come up with a decimal for me. Okay, go ahead and get pi in there and everything. Come up with a decimal for me. Tell me what you get. Anybody want to take a stab at it? No? Did y'all want to do this problem? There you go. 598.02. Good job. Now, let's go to this. So, in your book, when you start working the suggested homework problems and on your test, I will say use differentials, okay? But in the real world, if you're going to be an engineer or whatever, they're probably not going to say, hey, you need to use differentials on this one, because that's your job. They don't know that. So, when are you going to use differentials? Notice, every problem that we've done up until this point, look at our ordered pairs. This one, for example, we went from the point 4,1 to 12,9. That's a pretty big jump, yes? Here, we went from 1,1 to 2,8. Pretty big jump relative to what I'm about to show you, okay? But look here. We're going from the point negative 1 to 1.1, negative 1.331. Not a big move there, right? So, in Cal 1, we talked about differentials. Do you remember the delta y's and the delta x's? That's your tiny, 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 tiny movement. So, when you have a small movement, you can use differentials. Now, I will tell you, differentials are not as exact as integration. Integration is exact, okay? Minus the rounding, of course. Differentials, however, not so much. But you're moving such a tiny, tiny amount, that doesn't really matter, okay? So, look at your formula. You have ds is equal to the square root of 1 plus f prime of x quantity squared. So dx, of course. So if I ask you to use differentials, ds is the arc length. So we're not talking about surface area anymore. ds is arc length. And you're just finding the differential of the arc length. And notice it says to approximate. It says to approximate because this is not as exact as your integrals. In fact, if you do an integration on this problem, then you're going to get a better number, basically. You're not going to get, well, you might get close, but you'll be able to see the difference anyway. All right, so when are you going to use differentials? When you're only moving a tiny, tiny bit. So just keep that in mind. Again, on the test, I will tell you when to use differentials, but it'll be obvious because your ordered pairs will look like this. Okay, so for this one, notice we have y is equal to negative x cubed. So that is f of x, okay? So f prime of x, which is what we need for our formula, is going to be negative 3x squared. So, let's look at our formula. Here is your f prime of x. We just found that. F prime of x is negative 3x squared. What happens when you plug in? Watch this. When you plug in, you're going to get 1 plus, and we can go ahead and plug in our f prime of x, negative 3x squared dx. Well, normally, how would we get rid of our dx? What's the only way you can get rid of your dx? To integrate. Okay? We're not integrating. So we got to figure out a way to get rid of that dx. How would you get rid of your x's? By plugging in your boundaries. Okay? We don't have boundaries. So what are you going to do? Well, right here is x. X is 1. Dx is your movement. So from 1 to 1.1, what is the amount of movement? 0.1. Good. Now you're ready to go. So you have the square root of 1 plus, go ahead and do some algebra here. That's going to be what, 9x to the 4th dx. Plug in. So we'll have 1 plus 9 times x, which is 1 to the 4th power. And now dx is actually going to be 0.1. Maybe I should do it that way. All right, do the math. So 1 to the 4th power is 1. 1 times 9 is 9. So you have the square root of 10 times 0.1. Put it in your calculator and give me a decimal. What did you come up with? What? 0.32 is perfect. Okay? So, differentials are really, really easy, but they're not as exact. And the only time, please remember, the only time that you can use differentials is if you're moving a tiny, tiny, tiny decimal amount. Okay? Any other time we are going to integrate. And like I said on the test, I will tell you when to use differentials. But if I say use differentials, this is the formula that you're going to go for. And I don't think that formula is on your sheet, but look at your arc length formulas. Compare your arc length formulas to your differential formula. What's the only thing missing? Your boundaries, your integration symbol. And that's the two things that I told you that you weren't going to do with differentiate the differentials. Okay? So if you can relate ds to arc length, ds and L, they're the same thing, except L you're actually integrating and ds you're not. So take the integration symbol out and it's the exact same formula. So if you want to put that on your formula sheet, that's fine with me. So are we okay with differentials? A little bit easier, just not as exact. Okay. Next thing we're going to do for the remainder of the chapter, we are going to put our calculus with some physics. So for those of you who are taking physics or have taken physics, a lot of this is going to be cross-referenced. So once we finish this, you may say, hey, well, I can do this. No big deal. But for the next 3 sections, I think it is, maybe 2 or 3, I don't know. We are going to talk about some physics problems. Now, in physics, have y'all talked about work yet? Okay.
We're doing
Oh, okay. Well, work, if you remember back from physical science in 9th grade, for some of us that was a long time ago, for some of us not so much. Work is equal to the force times the distance. Remember that? Work is equal to force times distance. That is on your formulas page. Now, what we are going to do is we're going to look at work in 2 different ways. We're going to look at work as a constant, okay? And that's this formula, work equals F times D. How how do I know that? Work is a constant force acting on an object and moving it for some distance. So if your force is constant, it does not vary at all, then you have this. Work is equal to force times distance. Force times distance. Now, understand, work and energy are not the same thing. If I'm sitting here and I'm pushing on this wall, I'm exerting energy, but I'm doing no work whatsoever. Because I have force, but what am I lacking? Distance. Okay? So this is not work. I'm exerting energy, but there's no work being done. You have to have distance in order for work to take place. So if you ever see a work problem that gives you a force with no distance, the answer is 0 because there's no work done. Okay? So, in order to do just a constant work problem, you have to have a force, and I gave you an example here. Find the work done. So we know we're looking for work. Find the work done in pushing a car 20 feet. What do you think that is? That's your distance. Along a level road, exerting a constant force of 90 pounds. And then when you do the math, what do you get? 1,800, and this is going to be, actually it's foot-pounds. Now, one thing you may learn in physics, and I will tell you this here, this is one thing that helped me out tremendously in all through my physics classes, is those units. Some people look at them as they get in the way. Some people look at them as they help you set up the problem, and that's what I do. I let the units help me set up the problem, okay? If I know that work is in foot-pounds, or sometimes work is in newtons, that helps me know how to set the problem up, all right? So, constant force. Now, in the real world, rarely is there a constant force, because think about it. If you're pushing a car, and it takes a constant force from you of 90 pounds, and you're going to push a car 20 feet. Have any of you ever had to push a car? Ran out of gas, whatever? Yeah, me too. You know what happens over the course of 20 feet. You're not going to be able to exert the exact same force that what you started with towards the end of that 20 feet, especially if you're on a constant road. If you're going downhill, you might lose car. If you're going uphill, it's going to be even harder. So, this is not real world, honest, real world scenario, unless you're talking about mechanics. Okay? Mechanical engineers, you have the privilege of dealing with constant force, because machines, unless they tear up, they're going to give you a constant force. Okay? But humans, on the other hand, not so much. All right, so if you're dealing with a constant force, keep that in mind. Okay, because we're going to work a problem. We're going to actually work a couple of problems, but we're going to work a problem in particular that's going to have two parts. One is going to deal with a constant force, and the other one's going to deal with a variable force. Okay? So if you have a constant force, it's just force times distance. No big deal. So what happens if your conditions variate? What happens if your conditions go up and down, which is real world? That's when you integrate. Because what happens is when your forces go up and down, when your forces change because of your distance or because of your energy or because of whatever, when your forces change, you have to add those increments, and we call that summation. Back from Cal 1, what do we do when we have to do a summation? Not the sigma. Sigma is the same thing as what? Integration. Summation and integration are the exact same thing. Do you remember when I gave you your Chapter 5 test when we were learning how to do antiderivatives? On that Chapter 5 test, not only did you have antiderivatives, you also had summation problems. They're the exact same thing. Okay? Summation and integration are the exact same thing. So, when you have a variable force, what you have to do is you have to add together your increment forces, which is why we have the integral here. So if you have a variable force, just remember that this is the formula that you're going to use. Okay? So you have the integration from a to b, and then you have your function and dx. And of course, if it's a vertical, it's going to be gy dy. Okay? Just this formula is set up for a horizontal movement, but you do know that we can change the integration from c to d of gy dy if it's a vertical movement. Okay? No big deal. Okay, so the first one that I want to talk about, the most upfront one, the easiest one to get through your head to have a little bit of a visual, is work done on a spring, and we call this Hooke's Law. Hooke's Law is on your formulas page, but again, it is probably the most straightforward work problem that there is. So let's talk about some terminology. Your formula for Hooke's Law, like I said, it is on your page, is f of x is equal to kx. Okay, that's your formula for Hooke's Law. F of x equals kx. This describes the spring's behavior, I guess. Okay, so that's your function. That's what the spring is doing. If I had to plot it on a computer, or if I had to plot it on something, I would use that function, because you know function is just a graph. Okay? So, force is f of x, so make sure you know that. Anytime you're talking about force, that is f of x. So the force f of x required to stretch a spring, watch this, x units beyond its natural length. Every spring has a natural length. When you stretch it, you're going beyond. That's x. Now watch this. If you can compress the spring, it's going to be a negative x. Does that make sense? Stretching, it's going to give you a positive x. Compressing, it's going to give you a negative x. Okay. So x units beyond its natural length is given by, and there's your function. So what is this little k thing? K is called a spring constant. Have any of you ever done direct or indirect variation? That's where k comes from. When you do direct or indirect variation, k is that variant. K is your spring, is your constant. All right, so let's look at a problem.
The F in f of x, that doesn't stand for force, right?
No, f of x is your functional notation. That's the same that we've been dealing with since 112.
Right, and I never really, I know f of x is y, but...
This f is force. Okay. So if you want to look in your books on page 345, in your books on page 345, this problem is set up for you if you're a visual learner like I am. If I'm not mistaken, they may even have the spring, the picture, and everything on for you. Yeah. On page 345. There you go. Okay, so let's pick this problem apart and see what we can figure out. What we have here is this. A force of 9 pounds. What is that? What is 9 pounds? That's f of x. Is required to stretch a spring from 6 inches to 8 inches. Well, what do you think that is? What is 6 inches? Natural length. Good. Well, if it's telling you that it takes 9 pounds of force to stretch it from 6 inches to 8 inches, what do you think that is? What is that telling you? Very good. X is 2. So, x is equal to 2 because we're going from natural length to 8 inches. Now, listen to this, okay? That 2 required that 9 pounds of force. So, if we go beyond 2 inches, that 9 may go up, right? If we go beyond 2 inches, it may take more force because most of you know the farther you stretch a spring, the more force it's going to take, yes? And same thing with compressing it. So, what are we missing? We have f of x and we have x. What are we missing? K. K is your spring constant, and we don't know what that is, but we can find it. Watch this. I can use that spring behavior, this right here, maybe, yeah. To figure out what K is. Because you know what f of x is. What is f of x? 9. We're looking for K, and what is x? So what is K? So K is equal to 9/2. Now, what we're trying to do here is we're trying to come up with a variable work formula. On your page, do you know what a variable work formula would look like? If you have a variable work formula, it's on your formulas page. It's right there. You're going to have the integral from a to b, f of x dx. That's our goal. Because look, the problem says, find the work done by stretching the spring from its natural length to 10 inches. Okay, so let's go ahead and set it up. Work is equal to the integral from a to b. Well, what is a and what is b? A is your natural length. A is at rest. And you're going to think it's 6, but it's not. If the spring is at natural rest, it would be at 0. So if it's at natural length, it's not stretched, it's not compressed, it's at natural length, no force whatsoever. You're at 0. All right, but now we're going to go to 10 inches. So how far from normal is that? 4. Bless you. So you're going to integrate from 0 to 4. Mm-hmm. Natural length is always going to be 0. Okay, so now, what are we missing here? We have the integral from a to b, f of x. Do you know what f of x is? What is f of x? Do you know what k is now? F of x is 9/2 x. Because look, I just showed you and I just told you x can change, can it not? X can change. So I can't put 2 back in right here. The only reason why I used 2 was to figure out my spring constant. Okay? So when you go back to your function, you can put k in because it's a constant. It is your spring constant. X is going to change depending on how much force you put on it. X is what's varying depending on how much force you put on it. In this instance, it went 2. Okay? In this instance, it's going from 0 to 4. So you might think, oh, well, we'll just double it. You can't. Because every increment, every inch you stretch that spring, you have to add force. Okay? So you can't just double it. We don't know what x is right now. But we are going to integrate, and we're going to figure it out. Alright, so your function is going to be 9/2 x, and then of course we're going to integrate with respect to dx. Can you do that integral for me? Good. Good practice from Cal 1. Alright, so let's run through this. I'm going to move the 9/2 out front. You don't have to, but that's just what we've always done, so we'll just keep being consistent. And then when you integrate x, you get that. If you want to put those together, you can, or you can do your integration, whatever floats your boat. So we'll just be consistent and go with that. So 4 squared is going to be 16. 16 divided by 2 is 8. And of course, minus 0. That's nothing. And then what I would do is this. And so you get 36. What are our units? Not foot pounds. Inch pounds. Very good. Alright, so Hooke's law. You kind of sort of grasp it. First thing you got to do is when you're dealing with a spring, you're going to use Hooke's law. Okay? In Cal 3, you will have to do a presentation using anything in calculus from Cal 1 all the way through Cal 3 to work a real world problem. And if you look in the case on break, if you look in the case across the hallway, you'll see the previous Cal 3 students, that's the ones that they did. And some of them used Hooke's law. Coolest thing I've seen so far using Hooke's law is a girl she tore her ACL. And they went in and they were fixing her ACL and they have to stretch something or another. And she treated her ACL whatever as a spring and used Hooke's law to figure out how much work was done to stretch her ligaments back into place. It was pretty cool. She brought the video in and everything. I didn't watch the video, but anyway, so just be thinking about that. In Cal 3, you will have to use a real world application using any calculus that you want to. Alright, so again, Hooke's law, just remember when you're dealing with a spring or something that you're having to stretch, first thing you want to do is find the constant of that material, whether it be the spring, an ACL tendon, whatever. Once you have that constant, then plug it back in and come up with your function. Once you have a function, you plug into your integral and you go back to how we integrate. Okay? So, let's try another one. Same spring, okay, so you don't have to find the constant again, but same spring. So you're going to calculate the work. When you see that word, you should know which formula to use. We're talking about Hooke's law, and we're talking about stretching a spring. So are we going to use constant work formula or variable work formula? Variable work formula. Because the more you stretch the spring, the more force you're going to have to exert. So your force is not going to be constant. You have to know how to do that on the test. Otherwise, you won't know which formula to use, and that formula page is going to be irrelevant. Okay? So when we talk about work here, you are looking at this formula. That's your variable. It's on, for me, it's in page 3, I guess. Yep. But on the test, it's not going to say use Hooke's law. So that would be a good indicator. Good indicator. Okay. So now, calculate the work required to stretch the spring from 7 inches to a length of 9 inches. What's the only thing that's going to change here? Your boundaries. Yeah. X is going to stay the same because X, look, X is just your units beyond the natural length. And once we know K, we don't even need that anymore. Okay? Once you know what K is, you don't even need that anymore. So your function is going to stay the same. F of x is still going to be 9/2 x. Okay, so once you use the x to find k, leave it alone. You're done with that.
It's gonna be,
The only thing that's going to change is your boundaries. Can you tell me what your boundaries are going to be? And I will tell you they are not going to be 7 and they're not going to be 9. What are the boundaries going to be?
1,
Good. To what?
3.
Good job. You want to explain? Go for it. Why are your boundaries from 1 to 3? What? Start at 6, so 6 is 0. 7, you went up 1. 9, you went up 3. Okay? So, your natural state, whatever the number they give you, your natural state for your boundaries is going to be 0. And then if you stretch it, it's going to go up. If you compress it, it's going to go down. So for this one, natural state is at 6, but we're already starting at 7. So we already know that our lower boundary is going to be 1, because it's 1 inch past at rest. It's our natural length. Now we're going to look at it. And then 3 is the 9, it's 3 inches past at rest. Have you come up with a number with this one yet? Sabrina, you got a number yet? Now this one you're going to have to do a little more math than you did the last time because your lower boundary is 1. So Luke, you got a number? Very good. Very good. So what do you think? Hooke's law? Are we good? Just remember the initial x. They're going to have to give you information so that you can come up with an initial x so that you can find k. Once you know what k is, listen to my words carefully. Once you know what k is, don't ever substitute in for x again until you do your integration. Okay? And then your boundaries, just make sure you know how to get your boundaries. And remember, because there is a suggested homework problem where you compress a spring instead of stretch. The only difference is you're going to have negative boundaries instead of positive boundaries. Okay? Same calculation if you compress, except you will have the negative boundaries. Are we good? And just remember, when you're doing Hooke's law, on your formulas page, it just tells you that f of x equals to kx. You have to know how to figure all that out. And then also, you have to know how to use your variable force integration. Okay, before we go here, we definitely need to take a break. But we're going to anyway. Okay. All right, so we've already talked about this in a sense, but what we've talked about pretty much is like a two-dimensional direction, because if you're stretching a spring, you're on the XY axis, okay? So now what we're going to do is we're going to turn it into three-dimensional, and if we turn it into three-dimensional, it's a little, well, it's real world stuff, obviously, because we live in a three-dimensional world, but it's a little more hard to set up, I guess. A little more difficult to set it up. All right, so what we're going to do is we're going to turn what we know, W, work, in our variable integration from A to B, f of x dx, into a three-dimensional real-world functioning integral, basically. Okay? So, notice the comparisons, okay? F of x is going to turn into your distance, so we are moving. And then increment of force. Now, increment of force is going to be your change in force per increment. Does that help? So for every inch or for every foot that you move, the force exerted is going to change. So you're going to have to figure out what that incremental force is going to be. And I'll show you how to do that. So, okay. Increment of force usually is your weight. Okay. So here we have it. What we have here is a uniform cable. And I want you to get a picture of this, okay? In your brain. I'll draw one if you need me to. It's not going to be a Picasso, but hey. What we have is a building. And we have this little guy on the top of this building. And he's running a pulley. And the reason he's running this pulley is because he has a cable that is 30 feet long. And at the end of this cable, the reason why he's running this pulley, there's a beam, and that beam weighs 500 pounds. So let's go through the problem. A uniform cable 30 feet long and weighing 60 pounds hangs vertically from a pulley system at the top of a building. A steel beam that weighs 500 pounds is attached to the end of the cable. Find the work required to pull it to the top. Okay, so we are talking about work. Now, let's talk about a couple of things. Number one, if this cable is let out all the way, 30 feet, it weighs 60 pounds. So this little guy reels in this cable foot by foot. Is it still going to weigh 60 pounds as he reels it up? For example, if he comes up 15 feet, what's hanging over the side? Is that 15 foot of cable still going to weigh 60 pounds? No, it's going to be what? Half. Yeah, it's going to be 30. Okay? So, that's changing. Do you agree? The force exerted by the cable is changing per foot that it comes up. Now, why are we talking about feet? Because of this right here. Okay, if that had said inches, we'd be talking about inches, but since it's talking about feet, we're talking about feet. Okay, so we just discovered that as the cable is being pulled up, the work, the force, the work needed to pull the cable up is going to change per foot that it comes up. So let's talk about the beam, because that is the other force, right? We have two forces. We have the cable and we have the beam. Well, as that beam comes up with that cable, is the force that it exerts. Think about what force is. Force is your mass times your distance, or work is your force times distance. Force is thought of weight, mass, okay? As that beam is being brought up, does the work required to bring the beam up change? Forget about the cable. In order to bring that 500-pound beam up 30 feet, per foot that we bring it up, is the work needed to bring the beam itself up going to change? No. The weight does not change. The weight does not change. Think about how we just figured out the cable. We figured out the work changed for the cable because as the cable shortened, the weight lessened, right? Well, as that beam comes up, it's going to weigh 500 pounds no matter what. So its work, listen to this, its work is constant, whereas the cable's work is variable. Do you see where we're going? You're going to have to do two different integrations to find the work, and then you're going to have to add them together to find the total work. Okay? So, let's talk about this. Let's do the easy one first, of course. Let's do the work for the beam. Remember, constant work, your beam is going to be constant. So for constant work, all we need is force times distance. Force is the weight, or the mass, so what is force? For the beam, it's going to be 500 pounds. Times the distance, how far are we moving it? 30 feet. So for your beam, what are you going to get? $15,000 foot-pounds. Now the beam is constant, so that's why we get to use the easy one for the beam. Okay? Now, let's talk about the work needed for the cable. We know that it's going to be an integral because we've discussed that as you bring that cable up, the more you bring it up, the lighter it gets. Well, what are our boundaries? From what to what? How far are we moving? We're thinking about y-axis boundaries, okay? If we're thinking about y-axis boundaries, how far are we having to raise this thing? 0 to 30. Very good. Okay, so you have 0 to 30, and then we're going to have to integrate that distance. We're going to have to integrate that distance because per foot, the work changes. Okay, so we're going to have to integrate the distance. So your distance, whereas in the previous problems, your distance was just 30 feet because the work didn't change for the beam. But since the work's changing for the cable, you're going to have to integrate your distance. So why is it 30 minus y? It's going to be 30 minus however many feet you're bringing it up. That's what y is. Y is every foot that you bring it up from 0 to 30. Because that's what you're going to end up integrating. You're going to integrate that distance from 0 to 30. And y is going to take into consideration every foot that you bring it up. Okay? If we were going to do a summation, a sigma summation, we would do 29, we do 28, we do 27, and add them all together. But we don't have to do that when we integrate, okay? That's why we'd rather integrate than do the summation. Okay, the next thing we've got to talk about is the incremental force. The incremental force. Well, we've already talked about it, and you've already answered the question. We know that the force for this thing is 60, or the weight of this thing, I guess, 60 pounds per 30 feet. What would be the proportion per foot? What would be the unit ratio? What? So 2 is your incremental force. And then dy is where you're integrating your change in your height. So 2 is going to be your delta force. 2 is going to be your delta force. One more time. What is delta force? Delta force, this little triangle is delta. Delta force is the change per foot. Well, we know the initial force. When this thing's let all the way out, the initial force is 60 pounds per 30 feet. Well, for incremental, or the change in force, I need per foot. So for every foot that we bring this thing up, it's going to change 2 pounds until you get up to 0, which is going to be 0 pounds, right? So that's why you have a delta F. Now, the rest is Calhoun stuff. The rest you can do. It's just integration, right? So let's work on this. Why can I bring out front? The 2. Why can I not bring out the 30? It's grouped with that y. So we're going to have to integrate it. It is not a constant. That 30 will change depending on what y is. So you can't bring that 30 out. All right, so let's actually integrate. So we're going to have what? 30y minus y squared over 2. So what you got? Hopefully. All right, so plug them in. Thank goodness we have a 0. So we're going to have what? 30 times 30 minus 30 squared over 2. And then, of course, multiply that times 2. So what do you get? Anybody? 900. Very good. Okay, so we have the work needed for the beam. We have the work needed for the cable. So what is the total work required? $15,900 foot-pounds. And that makes sense to me because to raise a 500-pound beam takes a lot of work. A whole lot of work. All right, thing that's really fun. Let's look at this one. You have a right circular conical tank. What does conical mean? What's conical mean? It's a cone. It's just a fancy word for a cone. Okay. So you have something in your head so that you can think of a right circular conical tank of altitude 20 feet and radius of base 5 feet. Let's get a picture of this, okay? And it's very important to know that the vertex, if I could draw a straight line, that would be nice. Maybe I need a ruler. Okay. The vertex is at ground level. So the vertex is here. Really, is it? And it's a right circular cone, so I know that looks like that. It has an altitude of 20 feet. So here to here is 20 feet. And it has a radius of base 5 feet. So from there to there is 5. So that's why you get right, because you see a right angle. Not really going to come into play, but just so you know. Right circular conical tank of altitude 20 feet and a radius of base 5 feet. Now what I want you to do is in your head, I want you to imagine how big that is. Could you swim in it? Well, sure. It's as tall as the outside of this building. This building's approximately 20 feet tall on the outside because there's extra feet above there in the attic space. And then 10 feet diameter. So yeah, you can swim in this easily. Okay, so it's relatively big. Agreed? So what are we going to do with this tank? Number one, it's full of water. And that's important. And you need to know that the density of water is 62.5 pounds per feet cubed. This will always be the density of water. That's not going to change. I'm going to just cover up the cube. Not good. the test, if you are trying to move water, which is what we're doing here. If you're trying to move water and you need to know the density, what are you going to tell me the density is, or what are you going to use in your formula? 62.5. Okay? That's not going to change. Now, if I give you another substance, such as maybe tonight, maybe Monday, we'll deal with oil. Oil doesn't have the same density as water. I will give you that number. Okay? Water, I kind of sort of expect you to know. It's very important, especially for those of you who are in physics. You definitely need to know that. All right. So, if this tank is full of water, weighing 62.5 pounds per cubic feet, find the work done in pumping all the water over the top of the tank. Now let me ask you this. If we are going to take this thing that's full of water right now, and we're going to push from the bottom until all the water is gone over the edges. At the beginning, we're going to have to use a lot of work, yes? But in the middle, not so much. And then at the end, barely any at all, right? So as we move up this thing, let's take that little splice of water right there. As we move that little splice of water up, the less work it's going to take until it's filled over the top. And that's why we're going to have to integrate this. Now, let's go ahead and set this thing up. Your integral. Well, let's change back colors. What is your, well, first of all, let's talk about this. Are we talking about a vertical? Are we talking about the y-axis? Or are we talking about the x-axis? Are we talking about a change in the y-axis or a change in the x-axis? We're changing in the y-axis. We are talking about changing the y-axis from what to what? From 0 to 20. Okay, so there's your boundaries. Now, since you're using y-axis boundaries, what kind of variables do we need in our integration? Y. Okay, that's something that y'all tested on Monday, so you should know that. All right, so what's next? The next thing we've got to know is what? Our distance. Well, you just told me the distance, but the distance is going to change. Per foot that I go up, the work's going to change. So at 20, it's going to be one thing, but at 19, it's going to be something different. At 18, it's going to be something different. So y is going to be forever changing until this job is complete. So that's why you're going to have 20 minus y. And it's y because of what I just told you, you're using y boundaries. Now, this is the hard part. You're going to have to do the delta f. And the delta f for 3-dimensional is not as easy as the 2-dimensional. So, delta f, how are you going to do this? Well, force always depends on weight, mass, right? What is the mass of this water? What is the density of this water, no matter what? So that's part of it. I don't want to close that up. Okay. So you have 62.5. Now, let's say that we are only going to exert this work, this force, on that splice. That green splice that I drew in there. Because from the bottom all the way to the top, it's the same thing as if we were moving it all the way to the top, okay? Can you tell me what geometrical figure is that splice? It's a disc. It's a cylinder, basically, right? Disc, cylinder, same thing. Okay? So, since it is a cylinder, can anybody tell me the volume or how to find the volume of a cylinder? Close. Pi r, well, think about it, okay? Pi r squared is just the top or the bottom. So now how do you get the volume? There you go. So we're going to take our density, And we're going to multiply it times the volume of that cylinder. Okay? Before you start thinking too, this is easy. No, it's not. Because, look at this. I'm not tall enough to reach it. Look at your splice. The bottom of this splice. Typically, if we have a cylinder, your radius is going to be the same no matter what. Yes? But we don't have a cylinder, we have a cone. So the radius here is not the same as the radius here. What determines that radius? Well, you know the radius for this line is shorter than the radius for this line. What makes it shorter? The size of the cone. Those lines, the size of the cone. The volume of the cone? No. And the reason being is because I only need the volume of this one little bitty thing right here. That'd be nice. Okay, so volume is going to be pi. We know that, times the radius, that's going to be the hard part, squared. Height, listen to my words, height is always going to be either dy or dx. That's the easy part. Okay, height is always going to be your change in movement, or your change in where you are, change in position. That would be a good way to put it. Dy is going to be your change in your position. Okay, so let's figure out what the radius would be. This radius, you already told me, changes because of what? That slanted line. Well, do you know how to find the formula of a line? Do you know how to write, back from Algebra 1, Math 100, can you write an equation of that slanted line? In order to write an equation, you need to know two things. You need to know slope, and you need to know the y-intercept. What does that line cross the y-axis? At 0, so we're done with that. What is the slope? How'd you get it, Frank? Well, slope, I'm going to correct you on one thing, okay? Slope is rise over run. How much are we rising? We're rising 20 and we're running 5. So is your slope going to be 1/4? What is your slope going to be? 4. So that's the equation of that slanted line. Now, that 4x could be your radius if we needed x stuff. We don't need x stuff though, do we? What do we need? We need y stuff. So what are you going to do? What is x equal to? There's the 1/4. X is equal to 1/4 y. That's your radius. Okay, it's your weight. It's your weight times weight. Weight in this case is going to be your density. So it's going to be your weight times basically whatever geometrical shape you have. Because you have to multiply your weight times the shape that you're talking about. So the force of it really. If you multiply 62.5 pi 1/4 y squared, you're telling me the weight of that disc. Do you see that? This, okay, let's relate it to what we've been doing, okay? You have your distance times your delta force. delta force. Force is going to be your weight. So look, force is going to be your weight. So force is force times distance. So what you're doing is you're telling me the weight of this little splice here. To find the weight of it, you've got to multiply the density times how big of a shape you have. Does that make sense? Are you sure? Okay. So I don't know that it makes sense. Does that help? You're multiplying your distance times the weight of that disc. To find the weight of the disc, that's a disc of water, okay? To find the weight of that disc, you're going to multiply the density times how much of that disc you have. In order to find how much of the disc you have to use your volume. Okay? Is that better? Hopefully, maybe. Okay, the rest of it is a whole bunch of algebra. And then you have some calculus thrown in. So, yes? Yeah. Your height or your width. Either one that the formula is asking for is always going to be either your dy or your dx. Anything else before we move on? Okay. So, let's go with this. Do you see anything that I can move out? Yep, 62.5 pi for sure can come out. And there is something else, but let me do some math so that it will become more obvious to you. Now, does that help? Yeah. Why can I move the 1/16 out but not the 20? 20 is in a group. 20 minus y, it's a group with that. You're going to have to differentiate that. The 1/16 is a coefficient. It's a constant, so it can come out. So what we're going to have is 62.5 pi over 16. And we're going to integrate. Yes, thank you. That would cause some problems later on. Okay, there's one more algebra step that I want you to do. Do you know what it is? Let's distribute. And the rest is algebra. I'm sorry, calculus. All right, so we'll have 62.5 pi. If you want to go ahead and turn that into a decimal, you can, because you're going to do that in a minute anyway. All right, so let's see if you can come up with a number. 163,624.62 foot pounds. That's a lot. That's a whole bunch. And I will tell you that all the problems are not this hard, so don't let this problem make you run, okay? The only reason why I did this problem in this lecture is because there is one on the homework, the suggested study guide, whatever, that is somewhat like this. But if you can just follow step by step for this one, you should be fine. If I gave you a problem like this, it would be bonus points. A problem like this would be certainly for bonus points. So, again, don't let it panic you. Most of them will be like that problem or the one that we're fixing to do. The one we're fixing to do is relatively simple compared to what we just did.
You give us one like that, or you give us the volume of the shape that you use?
The formulas?
Yeah.
Sure. Okay. So let's let's just see if you can just set this one up. All right, if we set this up, and if you don't need a picture, that's fine, but you all know that I am a very visual learner. I have to have visual aids. Okay. So we know that this thing is 4 feet long. We also know that this thing is 3 feet tall. And we know that it's 2 feet wide. Okay, so there's your fish tank. And what we're going to do, now remember, we are going to find a sample splice. So there's our sample splice. Okay, so it's full of water, and of course we have the weight of the, or the density, however you want to look at it, 62.5 pounds per cubic feet. Find the work done in pumping all of the water over the top. Okay, so we're looking for work, and we're going to integrate. What are your boundaries? Good. Everybody should have got that. From 0 to 3. Very, very good. Okay, so what is the distance that we're going to have to differentiate? Very good. 3 minus y. So far, so good? Okay, because this is the rough part, and it's not as rough as previous, okay? What we want to do is we want to find the weight of that sample in red, okay? So in order to find the weight of that splice, that sample, what we're going to have to do is we're going to have to multiply its density. Let me do that over here.
Is the, we got 2 threes up there, is it always been like that?
As long as your figure is at the origin, yes. Okay. In the last section, we're going to move away from that. Either in these particular problems, we're assuming that the tank is completely full, and in the problems at the end of the chapter, we're going to change that. Okay. So as of right now, yes. Okay. So you're going to have your density, which is 62.5 times the volume. How do you find the volume one more time? Okay. So you have length times width times height. What are you going to get? See if you were listening. Somebody was listening. Length is what? Width is what? Height is what? Very good. Very good. So that one's not so bad, right? Hmm? Okay. We don't need an X in this anyway, at all. We could use a Y, I guess, but we don't need it.
So we don't use the 3 because the constant change.
Yes. Very good. That 3 is embedded in that dy. It's the change in your height, which is dy. Good. All right, let's work on this just a little bit. Can you tell me what 62.5 times 8 is? 500. Let's leave that out front, okay, because it is a constant. All right, and everything that I'm doing now is just pure Cal 1 stuff. So you should know how to integrate. Anybody come up with a number yet? Very good. Very good. Very good. Talk about another cool concept. I love this concept. You've got to have a visual of it, though, for it to make a little bit of sense. So this is called moments and centers of mass. What does that mean? A moment is just a tendency of moving a certain weight, mass, around a central point. That central point is called your center of mass. Okay? So don't get caught up necessarily on your words. Moments of inertia. Have you heard that? The tendency of overcoming inertia. How much force it takes to overcome inertia. Same thing. It's basically mass times distance. So if you can get that in your head, you're good. Mass times distance. Distance from the axis. And again, like I said, it's just the tendency of a mass to rotate about an axis. You've got to know the moments in order to find the center of mass. Now you can interrelate center of mass and center of gravity. Same thing. Center of mass, it's a balancing point. Okay? You're all familiar with a seesaw? In the middle of the seesaw, what do you have? Do you know the scientific word of the thing that's in the middle of the seesaw? You learned it in like 8th grade science? It's the fulcrum. It's the fulcrum. That's your center of mass. It's your fulcrum. Okay? So, what we're going to do is we're gonna go up. We're going to go from one dimension, which would be kind of like a seesaw, and then we're going to go to 2 dimension and so on and so forth. So, here you have it. And again, this is on your formulas page. Yes. This is on your formulas page. Now, I'm not sure why the powers that be chose to put the summations on here, because you're not going to be using the summations. Well, I guess you kind of sort of are, but it's in the problems that we're going to be doing, you don't necessarily have to use the sigma notation. Because in order to use the sigma notation, you would have to remember those formulas that allowed you to write on your formulas page in Cal 1. You know, the n times n minus 1 quantity squared over. Okay, so you're not, for these particular problems, we're not going to get that in depth. Okay, so anyway, the moment of S about the origin is m sub O is equal to your summation. That just means we're going to add each one of the entities, okay? Don't let that deter you. Don't let it throw you off. Don't let it scare you. The summation just means we're going to add. Can everybody add in here? Then that sigma symbol should not scare you, okay? Because that's all it means. You're just going to add these things. M sub K. M sub K is your mass. And then X is actually your distance. So you're going to multiply mass times distance, of course, from 0, from your origin. Okay? So in order to find the moment, that's what you're going to do. And remember, when I say moment, we're talking about a tendency to move a certain weight about a certain point. Okay, we're not talking about two totally different things. Okay, so in order to find the center of mass, you have to know what the moment is. So your moment is nothing more than the weight times its distance from 0. Okay, and when we're talking about one dimension, such as here, you're only going to have one number line, which means you're only going to have x values. But in a minute, we're going to have an x and a y, and so you need to keep that straight in your head. Okay, so the center of mass, and this is your fulcrum that we were talking about. The center of mass is going to be your fulcrum, and this is given by x bar. That's how you read that, x bar. X bar is equal to m sub O, which is what? What is m sub O? It's the moment. M sub O divided by m, which is your mass. Okay, m sub O divided by your total mass. M is total. Understand, M sub K is your mass at that point. M in your S bar is your total mass. So you're adding all of your weights together. Okay, so let's look at a problem. It says 3 point masses of 40, 60, and 100 kilograms are located at -2, 3, and 7 respectively on an x-axis. Find the center of mass. So what we're going to do is we're going to hang at -2. What do you think I'm going to hang? A 40 pound, or a 40 kilogram rather, weight? So what am I going to hang at 3? Good. And what am I going to hang at 7? Okay, so I want to ask you. You have all of these things on this scale. We'll just call it scale or seesaw, whatever you want to call it. If I had not hung any weights whatsoever, it would have been balanced, yes? And 0 would have been your center of mass. It would have been your fulcrum, yes? But when I hung that 40 pound over here, what do you think happened to the scale? It tipped. So now we're not in equilibrium anymore. So I tried to fix it by hanging the 60 pound. What happened? It tipped this way. So then I added 100 pounds and even made it even worse. But there is a point on this scale that will make it balance back up. Watch this. When there was no weights on it whatsoever, this was your fulcrum. Yes? When I added 40 pounds, my fulcrum had to go this way to kind of help lift it back up. Then when I added the 60 pounds, where do you think it would have to go? It's going to have to come back over here to help weigh it out a little bit. And then I added 100 pounds here. So let's go ahead and answer the question to the best of your ability. I want you to give me an educated guess. Educated guess. Find the center of mass. Find the fulcrum. Where do you think the fulcrum would have to be in order for this to be an equilibrium? 4, 5. Y'all agree? Disagree? Somewhere in that vicinity? Okay, so let's figure it out for real. Let's figure out exactly where it's going to have to be. All right, so the first thing you're going to do is you're going to have to find M sub O. You're going to have to find the moment. To find the moment, what you're going to do is you're going to multiply the weight times its coordinate. So tell me the first one. How would you set up the first one? The weight times its coordinate. 40 times -2. Very good. And we're doing a summation, so what does that mean? We're going to add. What would the next one be? Good. And then we're going to add, and what would the last one be? So you tell me, what is the moment? $800. $800. So did I find the center of mass? Because that's what the problem's asking you to do. I didn't find the center of mass, but I did find the thing that I need in order to find the center of mass. You need to understand that the center of mass is your X bar. So that's what we need right now. X bar, or your center of mass, or your center of gravity, is equal to M sub O. What is M sub O? What's your moment? divided by your total mass. Now we haven't figured that out. What is the total mass here? 200. So what does that equal to? Right? Bonus points for you, buddy. Right, here's your fulcrum. You hit it right on the nose. So 4 is your fulcrum. 4 is the center of mass. If you had a fulcrum at 4, this thing would balance back up. Can you think of some real world applications where this would come in? Aside from slinging your child off the seesaw? Playing with the seesaw? What?
Yeah, 60-40.
Yeah, definitely. Counterweights in anything, right? Have to have counterweights in just about anything. That would be a great real world use. And you have different size cranes. Have you ever wondered why you have different size cranes? Different size cranes, of course, will be able to handle different size weights, and of course, heights. Right? Okay. So this is one-dimensional. This is one-dimensional. Let's go two-dimensional. Okay, so when you go two-dimensional, you're talking about the XY axis. So you can imagine instead of having just an X coordinate, you're going to have an ordered pair. Okay? Because now you have to take into consideration the Y axis also. So when we're talking about two-dimensional, now watch this, and I want to see if you can wrap your brain around it. I want to see if you can offer me an explanation as to why this is. Okay? To find the moment of S, of whatever it is that they have there, about the x-axis. Watch. M sub x is your summation of your masses times your y coordinates. What? And both of you are saying the exact same thing. If we're talking about the x-axis, remember back on the previous page, it's the distance from 0. Well, if we're talking about the x-axis, it's how far you're away from, well, technically, because you're using the y-coordinates, how far you're away from the x-axis. Okay, so it's how far you're away from the x-axis. Because think about it. If you have an x and y axis, and we have some weight distributed maybe in the first quadrant, if we're going to say, if we want to take this thing about the x-axis, well, if you distribute a weight out here, out in quadrant 1, and we're only concerned about the x-axis, watch this. In order to get this to move, that's what a moment is, the tendency to overcome inertia, we're going to have to apply a y direction force. That y direction force is totally relative to your y coordinate. Same thing for your y-axis. You need to know the x coordinate. So make sure you understand that. If you're dealing with the y-axis, the m sub y, you need to know your mass and your x coordinate. And then, of course, your center of mass has to be an ordered pair. Has to be an ordered pair. So to find, go ahead.
Is there an example of that?
Yeah, we're going to do one in just a second. Real world.
I just don't understand that, yes.
Think about centripetal force. Have you talked about that in physics yet? Okay. Well, we're going to talk about, okay, well, we'll wait for the example and then I'll show you. X bar, in order to find your X coordinate of your center of mass, you're going to do my, your moment with respect to y, over m. Your total mass, again, m is total mass. And then to find your y bar, which is going to be the center of the y coordinate of your center mass, you're going to do mx over m, which again is total mass. Okay, so let's do this. Let's take this plane. Now you're going to have to use some imagination because we're not over in the, I would love to go over to the 3D theater and do this. One day when I have enough time, I'm going to do this. But what I want you to do is I want you to take that XY coordinate and I want you to turn it like this. I want you to turn it as though it was like this. Can you do that for me? If we don't hang any weights off of it whatsoever, where's the fulcrum? At the origin. It's at the origin. Okay. Well, the first weight that we're going to hang, and notice it says respectively. You understand what that means? The 4 goes with the -2, 3.
So this is like a top.
Elaborate.
You know, those little kids' clothes, little tops.
I think more of like a baby mobile, I guess, that hangs over a crib. How they can kind of get off. That's the way I think of it. Yay. Okay, so at -2, 3, we are going to hang, at -2, 3, we're going to hang a 4 kilogram weight. At 2, -6, we're going to hang an 8 kilogram weight. At 7, -3, we're going to hang a 3 kilogram weight. And at 5, 1, we're going to have a 2 kilogram weight. Okay, so here we have it. Take your X and Y axis, your X and Y plane, and turn it this way. And in quadrant 1, we have a little bitty weight. In quadrant 2, we have a little bit of a bigger weight. But where is most of our weight? Quadrant 4, we're extremely top heavy, bottom heavy, whichever, in quadrant 4. Okay? So if we're bottom heavy, top heavy, heaviest in quadrant 4, where do you think that center of mass, center of gravity, is going to have to move to help pull it back up to quadrant 4? Does that make sense to you? If most of our weight is here, okay? If there's no weight whatsoever, we're here. Yes, and right now, our center of mass is at the origin. So when we hang all these weights, when we hang that first weight on there, it's going to tip it in the direction of the quadrant 2. Then once we hang the second weight on there, which is at, what, 2, -6, it's going to go way down here because it's a heavy weight, right? It's the heaviest one of them all. So we still have a little bit of weight in 2, but then that quadrant 4, that 8-pound or 8 kilogram weight pulls it down this way. And then we hang a 3-pound weight in quadrant 4. Well, what's that going to do? It's going to make it even go farther. And then we hang another one in quadrant 1, which is just going to tilt it back this way some. So this is what it's done. So now, in order, where do I need, if I have all this, think of it this way, if I have all this downward force in quadrant 4, and I need to move my fulcrum from the center of the origin to help push up to level this thing back up. Which quadrant do I need to move to? Quadrant 4. Because look, it was at the center, and now we're heavy in quadrant 4. So to help move it back up, I need to move it.
So what about this?
Mm-hmm.
It makes instead of like.
Yes.
Okay.
Yeah, because you have the downward forces from the weight, so our fulcrum is to help equal it back up. Okay, so do you have kind of sort of a mental picture? Better than before, maybe? Go online. They've got some cool stuff online to look at. All right, so let's start doing some calculus on this. The first thing that we need to do is we need to find m sub x. Can you tell me the formula for m sub x? M sub x is what? It's the summation. It's the summation of your weight times what? The y coordinate. Don't forget that. Times your y coordinate. All right, so the first one is going to be what? 4 times 3 plus 8 times negative 6 plus 3 times negative 3 plus 2 times 1. Come up with a number for me. Anybody? Negative 43. Good. Okay, m sub y. How are we going to find that? Your weight times what? The x coordinates. Come up with a number for me. $39. Okay. Now, to find x bar, we need what? M sub y, good, over m. We don't know what m is yet. What is m? Has anybody figured it out? What is the total mass? 17. Good. All right. So x bar is going to be 39 over 17. Y bar is going to be your m sub x over m, which is going to be negative 43 over 17. You're going to add 4, 8, 3, and 2, all of these together,
Oh, okay.
because it's your total weight. All right, so your ordered pair is 39/17 and negative 43/17. Does that mean anything to you? Could you graph that if I asked you to? You could, but what would you have to do? So what are you going to get? 2.3 and negative 2.5. Now let's see, where did we say that it was going to go? We said that it was going to go into quadrant 4. Let's see if it actually did. 2.3, negative 2.5. What do you think? It's about right there.
This right here, work in the real world, we actually demonstrate this.
Yeah, and like I said, if I was in the 3D lab, we could really have some fun over there.
I like this.
Can you kind of sort of see what's going on? Kind of sort of wrap your brain around it. If you want to go into the book, you can. Personally, so if you look on page 352, you can kind of see what's going on. On page 352, you can get kind of a visual aid, I guess. Okay.
And these formulas,
Are they not? No, they're on your. They're on.
New one?
I don't understand why are they on mine and not on yours? That does not make
Is it front and back?
mine is.
See, but I know like printed out like 2 pages.
yeah, but it's two front pages.
Less than I have a year. I don't know.
Yes, yeah.
The word.
See, there should be moments and center of mass should be